So for 4c refraction, just starting by looking at an example of what can happen if refraction actually occurs with light. So quite clearly this person's head is not detached from his body, but what's happened is something to do with the light that's reflecting or bouncing off his head and coming straight to our eyes, and then obviously the light that's leaving his body, which is inside the water, and then making its way to our eyes, has actually changed direction somehow, so it looks like his body is over there, whereas his head looks exactly where it should look. Okay, so just very quickly, refraction is something to do with the changing direction of light when it goes in different materials. So you've got water and you've got air. The fact that we know his head is exactly where it's supposed to be is because we know that the light from the sun has bounced off his head in air, traveled straight to our eyes in air, and therefore hasn't changed medium, it hasn't changed substance, so it's traveled through the same material from the sun to his head to our eyes in a straight line, which means that the line that we see the light for his head is in the right position, it hasn't changed direction. What's happened to his body? So the light from the sun has actually come down into the water, it's gone into the water and it will have changed direction, it's reflected off his body, so it's on its way out of the water, which means it changes direction again, and then it comes into a straight line in our eye in a completely different direction to what it should have. So because it's gone into water and out of water, the light actually changed direction, and therefore the line in which the light enters our eyes is a different line to where it should be, so it looks like it's in a different position to what it should be. So basically the effects of refraction, what they can have on what we see, is the light entering our eyes in a straight line from a different position than it should be because it's changed direction, and then it looks like things are in the wrong direction. So we need to know explicitly what is refraction and why does it occur. So first of all we're going to take a look at this perfect example of how light can change direction when it moves from one material to another. A few things that you need to know and need to be able to define before you have a full understanding of why refraction takes place is, first of all, different mediums, so different materials, have what we call a different refractive index, and that just tells you how much does it make the light change its speed, and depending on how it changes the speed of light will depend on how it changes direction. So if you look in this one, this first example, you have light traveling in a straight line which is explicitly perpendicular to the water surface or the boundary. Now this is a very special example because the boundary of water to air is here, so it's horizontal, and you have air above water or glass below, and you have the light ray coming perfectly perpendicular. So if you've got the boundary of the water here and the light comes in perpendicular, you can see that actually it doesn't change direction. So refraction doesn't occur if the light ray is perpendicular to the boundary. And the reason is, although the speed will still change, so if light travels from air to glass or air to water, then the speed of light will slow down. Now it has still slowed down in this example, but because it's perpendicular, the direction doesn't change. But if we take the same example again, where we've got light traveling from air into glass or water, so first of all, glass and water have a higher refractive index than air, which means they will cause the light to slow down when it travels from air to glass or air to water. So we could say, in this example, light is going to slow down at the boundary, and if light slows down at the boundary and it comes in at an angle to the normal line, so as you can see on these diagrams, the normal line is a dotted line that goes perpendicular to the boundary. So if you ever want to draw a normal line on a ray diagram, your normal has to be, we usually draw it as a dotted line, but it has to be 90 degrees to the boundary. So for example, the boundary again is horizontal, that means the normal line is 90 degrees vertically to that boundary. Now if the light ray is coming in at an angle, which wasn't the case in this one, but in this one it's coming in at an angle, what you can see happens here is it changes its direction inside the glass or inside the water, and it's actually changed its direction towards that normal line. So as you can see, it's closer to the normal line. So a definition for this example could be, when light travels from one medium to another, from low refractive index to high refractive index, the light slows down. So if the light slows down when it crosses the boundary, it changes direction towards the normal. So here it's slowed down. If it slows down and it comes in at an angle, it has to have an angle to the normal. It can't come in perpendicular to the boundary or along the normal line. Okay, it has to come in at an angle, and if it slows down, it goes from low refractive index to high refractive index, then it will change direction towards the normal line. All right? Alternatively, if we looked at this the other way around, so for example, here's the normal line again, you've got your water to air boundary or your glass to air boundary, which in this case is glass, so light is traveling in glass and it's going to move to air. The boundary is horizontal, that means the normal line is vertical as it's 90 degrees to the boundary. The light is actually coming in at an angle to the normal, so it's not coming along the normal, so it is coming at an angle, so we know it will change its direction. But as it's going from glass or water to air, you're going from high refractive index to low refractive index. Or, when it travels from glass or water to air, we know that the light is going to speed up. And as you can see, if it goes from high refractive index to low refractive index, then it changes direction or it refracts away from the normal. Alright? Alternatively, you could say if the speed of light increases, so it's going to speed up when it leaves the water or the glass to air, it will speed up. If light speeds up, then it also refracts or changes its direction away from the normal. So two examples, low refractive index to high refractive index, light refracts towards the normal. High refractive index to low refractive index, light changes direction or refracts away from the normal. Or we could say, if it travels from air to glass and slows down, so if light slows down when it crosses a boundary, it changes direction towards the normal. And if light speeds up when it crosses a boundary, so it gets faster, then it changes direction away from the normal. So in all of those examples, we are always referring to the normal line and how light changes its direction compared to the normal. If light were traveling 90 degrees to the boundary or along the normal line, then there will be no change in direction. It will still change speed. It still slows down in the water. It could still be going along here in the glass or the water and coming out of the air. If it was traveling along the normal, it would still speed up when it left, but it would not change its direction. It has to come in to the boundary at an angle to the normal. Now what we call this angle, we always measure the angle of the light ray from the normal line to the ray. So this angle from this normal line to the ray here is called the incident angle, and therefore when it's refracted through the boundary, in this case remember it's slowed down, it's gone from low refractive index to high refractive index, so it changes direction and refracts towards the normal. The angle between the normal and the ray on the inside is known as the refracted angle. Alright, so this one here, normal to ray before it enters, is incident angle. Incident means it's coming in, and the angle between the normal and the ray once it's refracted inside the new medium is known as the refracted angle. Alright, to get an idea of why, so we've said what happens, we've said if it goes from low to high refractive index, which means it slows down, then it will change its direction towards the normal. If it goes from high to low refractive index, i.e. it speeds up, then it will change direction away from the normal. But we don't actually have an explanation as to why. Why would light change direction in that specific way if it slows down or speeds up? And this is a perfect example and a perfect analogy to help explain why is it changing direction and why is it changing direction in the way that it is. Alright, so if we look at an example where we have smooth pavement or road where a car would normally drive, and we have this car driving in to a boundary between the smooth pavement and then a muddy or sandy surface. So you have smooth surface where obviously the car can drive a lot faster, and then it's going to hit this muddy surface where when it hits from smooth to muddy, it's going to slow down. Right, so the first thing we need to note is that it's going from smooth to muddy, which is faster, and when it hits the mud, it will slow down at this boundary. Now, we draw a normal line just as we did in the ray diagram before. We draw a normal line which is perpendicular to the boundary. Since the boundary is horizontal, the normal line is vertical, it's 90 degrees. Same would happen if you had a boundary that was vertical. So for example, you had a glass block which was vertical, and the light actually came in horizontally, then your normal line would be a horizontal line, because if the boundary is vertical, the normal line has to be 90 degrees to that, which would be a horizontal normal. So all you need to do is, sometimes you get a boundary which is actually at an angle. So if this was the boundary at this angle here, then your normal line would just have to be 90 degrees to that. So it would actually be at an angle itself. Just as long as those two lines, the boundary and the normal, are 90 degrees, then you have no problem. So the normal line in this example again is obviously vertical, 90 degrees to the boundary. I know the car. The reason this is a really good analogy is because the car actually has a width. It has a wheel and a tire on the left hand side from our perspective. So on the left hand side it has a tire, and on the right hand side it has a tire which is a certain distance away. So it actually has a thickness, if you want. Now what's going to happen, we know that it will slow down, but what's going to happen, because it's coming in at an angle, this tire on the left will slow down just before the tire on the right. So because the left-hand side of the car slows down before the right-hand side of the car, this one slows down. This one on this side actually carries on traveling at a faster speed just for a short moment of time. So if it's coming in at an angle and this one slows down first, what's going to happen is this one on the outside is actually going to take over. It's going to travel faster for a short period of time, and it's going to turn the car slightly again towards the normal. So if light slows down, it means that one side of the light, which we're going to look at in a second, one side of the light slows down first, the other side carries on at a faster speed for a short period of time, and it actually takes over and turns the object, the light, the car, it turns it towards the normal until it reaches the mud itself, and now it will travel through the mud, the tires on each side at the same speed. It's slower, but it's changed direction at the boundary, and now it's going to pass through the mud at that angle at the same speed. So the reason refraction occurs, if we quickly look at this example here for water waves, we've drawn these water waves as parallel lines, which are called wave fronts. Now these wave fronts are the width of the waves themselves. As you can see, the red line through the middle is known as the ray. So when I draw a light ray such as this, I'm not saying that light is just one thin line without a thickness left and right. I'm saying this is just showing me the direction that the energy and the wave is traveling. Okay, so a ray is not just the wave itself, it's just showing me which way is the energy being transferred. Now if I look at a proper wave, what the wave should look like, you have a thickness. You've got these wave fronts which are parallel lines with the ray that goes through the middle. These wave fronts have a left-hand side and a right-hand side. They have a width, just like the car. Now, if we reach the boundary, which in this case is vertical, so the boundary is vertical, the normal line, as you can see, is horizontal. It's 90 degrees to the boundary. These wave fronts are going to hit the boundary at different times. In this example, the right-hand side of the wavefronts hits the boundary first. The left-hand side of the wavefronts will actually carry on traveling at their initial speed for a little bit longer. This example is actually deep water to shallow water. So they're water waves, not light waves, but the same thing applies. So deep water, you have the wavefronts coming in. This part of the wavefront hits the shallow water boundary first, which means it slows down. So water waves actually travel faster in deep water, slower in shallow water. This side of the wavefront slows down first, meaning the other side carries on faster for a short period of time, turning the wave towards the normal. So if water waves slow down at a boundary, but at different times, because as you can see it's coming in at an angle, if it came in along the normal, it would slow down, but it would keep going in the same direction. Okay, so because they're coming in at an angle, this side of the wavefront slows down first, the other side carries on for a short period of time, it turns the wave, it changes direction, it refracts towards the normal, and then it will carry on through the water in this direction. So going back to the light, in this example you only have the ray, you don't have the wave fronts. But if I were to draw on those wavefronts there for the light, as you can see we've got the parallel wavefronts coming in. It's coming into the boundary at an angle. is coming from air to glass or water, which means it's going to slow down. This part of the wavefront slows down first. This side of the wavefront carries on for a short period of time at a faster speed. That means it turns the light ray towards the normal. So if they slow down, they turn towards the normal. If they speed up, the same thing applies. So here you have your wavefronts again hitting the boundary from water to air. This side of the wavefront will leave the boundary first, meaning it will speed up first. So this one is high refractive index to low, they're going to speed up. This side of the wavefront will speed up first, meaning that it's going to take over the other side slightly until this one leaves, turning the wave away from the normal. So if it speeds up first, it turns away from the normal. But if it slows down first, then the other side turns it towards the normal. So the reason and the explanation as why does light, or why do waves in general, change their direction when they cross a boundary, and it has to happen at an angle, it will not happen if they come in. And the reason for that is, if I were to draw my wavefronts on this one, you can see they come in at the same time. So they actually cross the boundary at the same time. The left and the right cross the boundary at the same time, which means they will slow down together and they will just keep moving in the same direction. No one side of the wavefront is actually traveling faster or slower at any time, so why would it change its direction? Nothing will overtake the other side. In this one, this side slows down first, so the other side carries on faster and turns it towards. In this one, this side speeds up first, so as it speeds up first, it actually turns it away from the normal. Okay? Again, the analogy we used was the car. You have a left side and a right side, and if one side slows down or speeds up first, then it will change the direction of the wave. There is one more thing to note. If you look at this wave, this is water waves from deep water to shallow water. And because the normal line is horizontal, that means the boundary from deep to shallow is vertical, so they're 90 degrees to one another. The wavefronts of the wave are the important part which tell us why refraction occurs. So if we've got the wavefronts here, they have a gap between them, and we know that the gap between the waves is known as the wavelength. Now, in this example, when the wavefronts slowed down first on the right hand side, so they reach the shallow water first, they slow down on this side first, that means this side carries on traveling faster for a short period of time. When that happens, the waves turn towards the normal, they've refracted at the boundary, they've changed their direction towards the normal, they'll continue to move in this direction together. But if you've noticed, these wavefronts actually have a slightly smaller gap between them. Now if this is the wavelength of the wave before, this must be the wavelength of the waves after, and what you can see is if their waves are closer together, their wavelength must have decreased. Now, the only reason for that happening, if we have a look at the equation, we know v, the speed, is equal to the frequency multiplied by the wavelength. Now what we need to know is that the frequency of waves when refraction occurs, so when they come to this boundary and they change their direction and they're now traveling at a new speed, slower in shallow water, the frequency of those waves remains constant. It's exactly the same for light. If I go back again, when they slow down in the water or the glass, the frequency remains constant. The frequency of light is the color, and the color doesn't change if it changes its speed. So the frequency of light remains constant inside the glass. When it changes from one medium to another, the frequency does not change. However, the speed changed. So if I go back and I look at this equation again, if I rearrange this equation for f equals speed divided by wavelength, and I know that the frequency has to remain constant, if the speed changes, the wavelength has to also change. Now in this example, if speed goes down, because it's a fraction, if speed goes down, then wavelength must also go down to keep the frequency the same. So this is a really important part of using the equation and thinking about why does the wave change and how when it moves from one medium to another and it changes direction and speed. So if the frequency remains constant for water waves, the frequency remains constant for sound waves, it also remains constant for light. Then if the speed goes down, it slows down, the wavelength must also go down. But if the speed goes up, for example, in this situation here, we know that it's going from glass to air, from water to air. It's going to speed up when it crosses the boundary. If the speed goes up, then the wavelength must go up. Frequency remains constant, speed increases, and therefore wavelength also increases. And that is as much as you need to know for refraction.